and then you consider each basic block at a time. That is the most common way of doing the scheduling. I mean, doing the hardware design is you take one basic block at a time and you try to find out a very optimal design for that, and then you combine the the resource of the multiple basic block, share the resource that is that you identify for each basic block, and you try to combine them and share them, right? That is the overall idea that we have discussed. And then we have seen that for this high level synthesis, first step is pre-processing, and then you do all this stuff, and then you take each basic block and do the scheduling, right? The scheduling is basically identify or decide the time step of each operation, so where to execute each operation. That is what is called scheduling. And then based on the scheduling, you identify how many registers we need to map those variable into the registers, that is the register allocation and binding. And then you try to identify how many function unit you need, and then you map those operations into those function unit, which is called a function unit allocation and binding. And once that is done, that allocation of registers and function unit is done, I already obtained the register transfer level behavior, right? And then what we can do, we can just from the register transfer level behavior, we can actually make the interconnections, what is called data path synthesis. So based on the connection requirement, and we have to do time division multiplexing, we have to add multiplexer, adder, decoder or demultiplexer in the designs. It may be switch space, mark space, anything. Your data path is done, and then based on the connections and the signal propagation, signal that is needed in each time step, we have to design the controller. Right? So the controller will decide which operation to be executed in which time step, right? So that is what we have already understood. So I hope you have the that you have a very good idea now what is the high level synthesis and how these steps is taking place and what to do. So what is the objective of now is basically we'll take each of these operations, say scheduling, allocation, binding, data path generation, controller generation, and we'll see what are the kind of problem we have to solve here and how to automate the process. What is the common algorithm that are getting used. These things we are going to discuss now, right? So specifically, we are going to discuss some part of the scheduling today. Okay. So feel free to stop me and ask questions in between whenever you have any doubt. So in today's class, we'll primarily decide we'll formally define what is scheduling, and then we'll see what kind of scheduling problem we have, and then we'll take one of the type and try to see what are the solution we have. Okay. So first of all, as we discussed in the last class, previous classes also, that when you do the scheduling, you need a data flow graph. The data dependency is needed, right? So, and we have already seen how to obtain that data dependency graph, right? So it's basically the dependence based on the data flow. So the model that we are going to consider is basically sequence graph, okay, or sequencing graph. So what is sequence graph, and how to obtain that from the data dependency graph, right? So that's something let us understand first. So if you remember in the example that we have considered in our in the previous classes, we take that data flow graph. So this is the dependence graph that we obtain. I hope you remember. So it means that this operation depends on these two operations. So basically this has to be done, then this can be done, right? So this is what is the data flow graph. So now the question here is that, so what we're going to do is see if at the inputs there are many inputs, right? So there are many variables. So we may not need all those detailed information for our scheduling, right? Because in scheduling, what is important? The operations. These operations are important for us, right? We don't need these inputs and outputs. To make the graph simple, in the sequence graph, what we do, we just do not need to understand how many inputs are there, what are the inputs. We'll just say we'll just merge these inputs into a single node, right? So we merge this node into a single node, which is, you can tell, is a source node, right? This is source basically. So this is source node, right? Similarly, it may have multiple outputs. I can merge all those outputs, whatever the outputs are there, into a single node, which is called sync node, right? So this is what is called sync node. So that I actually simplifies this graph into this, so that I can assume that this graph, this is the common source node and this is the common sync node. Nothing, this is just the representation purpose. Nothing much to worry about this. Just to make the graph simple and only keeping the relevant information with us. Right? That's the only thing. And what we can assume that since we decide the time step, say this is my time step 1, this is my time step 2, this is my time step 3, and this is time step 4. We can assume that source node is always getting decide on the time step 0, right? So basically, when you consider the scheduling, you have to schedule the source node as well. We can always assume that this is always scheduled on time step 0, and whole process starts from time step 1, 2, 3, and 4. Right? This is how I can think. And then whatever the time I obtain here, so say this is the lambda, so this will be lambda plus 1, right? So this is lambda plus 1, where my sync node will be presented, but my schedule time is basically lambda. So one more terminology is very important here, it's called latency. So you should understand, for a circuit, always you have to understand what is basically latency, right? So latency is basically the time or the number of clock is needed to execute a behavior, right? So you give a input when you are getting the output. So that is the difference from the giving input versus obtaining output corresponding that input. That difference, time difference, is called latency. So in context of scheduling, it's basically, if somebody say your latency of this design is 4, that means it's basically taking 4 time step, right? So in this particular example, if I give some input at say time step 1, so then it is basically after 1, 2, 3, 4, after 4 time step I am going to get the output. So it's basically the latency of the design is basically 4, and what is that? It's basically the number of time step needed. So in context of digital design, latency is very important term, which we'll explore further, because when we think about a pipeline design or a say unroll design or a data flow design, the latency is not the simple the way it looks, right? If it is a pipeline design, it may be that once you give an input in time step 1, the first output, say the number of pipe stages is 4. So first output will come after 4 time step, but that after next time step, 5th time step, will get the second output, third, the 6th time step will get the third output, and so on. So the latency of that particular pipeline design is basically 1, right? Because I mean, after the initial that one, once the pipeline stages are filled, every clock you are going to get a output. So latency is not always like whatever the time step, it based on the design, when the way you design the circuit as well. But when in the context of scheduling, so in the context of scheduling, we need only this in the context of scheduling, we only need the time step needed. Okay, so I hope you understand what is sequence graph and what is the latency. Okay, so the circuit model, as I told you, that it is basically a sequence graph, and then the assumption is that the cycle time is fixed. So we can assume that every clock is fixed, say 100 megahertz or 200 megahertz or 50 megahertz. So that is fixed. You do not have the clock timing is free, variable, right? So that is fixed. And then this operation delay. Yes, please.
Excuse me, sir.
Yeah.
So in the previous sequence graph, can you just move to that slide once?
Yes.
So like based on the dependence graph, the sequence graph is not in exact correspondence. Like V3 there has no dependency, so it is moved to
Don't go into that delay. So I just copy paste from 2 different source, and don't worry. So it's basically same. So the internal structure is as it is. I just copy paste from 2 different source. I mean, basically what the only difference is that you remove all the individual inputs and you put a single node as source, and all the outputs you remove and put a single output node as sink, and rest of the things are remain same. So data dependency I'm not touching, although it's not showing same because when I copied from two different sources, but that is not important. Important is how we merge the inputs and output. Okay. Okay, understood.
Yes.
Okay. So now so the cycle time is fixed, is understood. So the next point is basically this. Just a second, I have a call. Hello. Yes, tell me. Yeah, tell me. Hello. I'm sorry. I just switched on my phone. Yeah, sorry. Yeah. So let me go to this. So now the next thing is the operation time. So far the example that I have taken in my this in the example that I have shown in the previous classes, we always assume that one operation is taking one cycle, right? But that may not be the case. Okay, because in some time, say for example, in this example again, if I take the example again, this some operation may be two cycle, right? So the number of times taken by a operation is may not fixed. Say for example, this adder might take one cycle, and this multiplier might take say three cycle to execute. Right? So there is a trade-off here. I can tell you. I'll tell you the story why we need to consider this kind of thing. Say so if you think about a multiplier, you just think about a design of multiplication. So how many additions and addition you have to do. So every time you say there are two n-bit number, so there are basically in number of rows in the will come in the multiplication table, and then you have to add it, right? So many multiplication is happening, so many addition is happening, right? So obviously a multiplier is much more complex circuit compared to adder is single addition. So one multiplier may have say many number of addition and multiplication of small numbers in between, right? So in the high level this multiplier is much more complex operation than an adder. So now you think about but obviously if you think about if you have to do more, you need more time, right? So if you need more time, how do you do that, right? So the concept is this. So suppose your clock is coming like this. So this is your clock, right? So this is your clock, and this is basically your one. This is one clock. Right? This is the one clock period. So this is the time you will get to execute the operation that is scheduled in a time step, right? So suppose now in this one clock, say multiplier and adder both are scheduled, right? So suppose you want to execute a multiplier and an adder, and I told you that this multiplier is at least 10 times complex than an adder in circuit wise or time. So that means if say this adder takes a 1 nanosecond to execute, then this multiplier need 10 nanosecond. Okay. So since this clock, both you have to do this multiplication and addition in one clock, that means you need to put at least 10 nanosecond because you need to execute the multiplier. So that means the adder will remain inactive or doing nothing for 9 nanoseconds. Right. So that means if there are more complex operation than multiplier, and if you want to execute them in single clock, your clock period will be more, right? So that gap, this gap between the clock period, right? This is one clock period. So the clock period will be more. That means clock is slow, right? So whenever this basically clock speed frequency is 1 by clock period, right? So if it is 1 and 10 nanosecond, so 1 by 10 nanosecond is basically 100 megahertz. The clock speed will be 100 megahertz. If it is a 5 nanoseconds, so 1 by 5 nanoseconds is 200 megahertz, right? So obviously you understand. So we want to run clock faster, right? The, so here the trade-off is that if you want to make every operation is a single cycle, your clock speed will be slow, right? Clock will be slow. Clock frequency will be slow, right? So it is basically 100 megahertz. This is 200 megahertz. So obviously there is a trade-off. The point here is that if you want to run the things faster, so suppose I want to run this particular design in 200 megahertz, that means my multiplier cannot be done in one clock. So what I'm going to do now? I'm going to do this multiplication operation in two clocks. So I'm going to do this multiplication in two clocks. Right? So then multiplier become two cycle operation. So that means whenever I schedule a multiplier in this clock, my multiplier will be remain blocked for two clock cycle, and but adder I can complete it here and I can do the next addition operation here. So that means, so in this, so the advantage is that earlier if I want to run it in say 100 megahertz, I have my 9 nanosecond time my adder is idle, or I could have done something, I am not utilizing the time. So if I split that multiplied into two cycle, at least now I can do two operations, two addition operations instead of one. But I need two clock. So but the time is same, right? So I need till 10 nanosecond, but my clock is running faster. That means whenever my next clock comes, I can do the other stuff in other. So other lightweight things can be done, whereas this operation will continue for multiple cycles, right? So in general, in hardware, this complex operation like multiplication division is not a single cycle operation, and I just give an example of two cycle, but it can be four cycle, five cycle operation. Okay, so that is what is basically talked about, is the delay. So each operations, you have a delay, or the number of time step or number of cycle it needs to complete the operations. In very simplistic case, you can assume all the operation is single cycle. That is what I have considered for my example in the previous classes. But in general, they can be multiple, I mean they can take multiple cycle, and which is basically practical, so that I can have a higher clock speed. Okay, so this is my circuit model. So I have given the sequence graph. I know what is my kind of clock time or the clock duration, which is something fixed. And I also now know for each operation what is the delay involved, how many cycle it takes to complete. Okay. So once that is given, what is scheduling? Scheduling is basically determine the start time of each operation. Why start time? Because if I know the start time, and if it has say if I schedule a operation in say time step 5, if I know it is basically take a 3 cycle operation, so it is 5, 6 and 7. So I know that if the start time is 5, the operation is going to execute in time step 5, 6 and 7, right? So scheduling informally determines that start time of each operation. Okay, and obviously satisfying all the resource and timing constraint. Okay, so whatever the constant is given, so sequencing constant is already given. The sequence is basically this, the data dependency. So it should satisfy the dependency constant, it should satisfy the timing constant, it should satisfy the resource constant. Okay, and obviously it's not that if you just I mean satisfy the constant, you try to obviously optimize or minimize the area or latency, whatever the your objective is given. So as I mentioned, that latency and area is basically vice versa. It means if you try to optimize the area, your latency will increase. If you optimize the latency, your area will increase. If you ask me why, because if you want to do say suppose you want to increase the latency, that means I want to execute as many as things in one cycle, right? So that means you have to put more operation in parallel if it's possible at all, so it satisfies the resource constant. Then your area will be more. So suppose there are 4 adder you can execute in one cycle, you need 4 additional adder units, and if you want to execute in a 4th cycle, you need only 1 adder, right? So 4 cycle versus 1 cycle. So obviously your area will increase if your latency goes off, I mean improves, and if your latency decrease, you can actually reduce the improve the area's performance. So this is basically a trade-off between this. Okay. So once you do the scheduling, you have to keep keep your eye or your objective open on these things. Okay, and based on this optimization constraint, you can have different kind of scheduling. So here the example that I have tried to put here is basically scheduling is assigning time step, which you already know. But so scheduling in general is this, that you decide the time step for each operation, so the start time of each operation. So the way I have shown the graph here is single cycle. but you can have, say, for example, this multiplier says a 2 cycle, so this will take like this. So if it is a 2 cycle, so this multiplier will be scheduled like this. Sorry.
Excuse me, sir.
Yes, please.
Sir, is there a limit on how small we can make the clock period?
Yeah, so it depends on the combinational delay, right? So suppose if you consider this particular design, so now you know that I need to execute on multiplier, right? So your circuit clock speed will decide the delay of this by the delay of this multiplier, right? Because if this is the schedule, you have this four, basically in every step we have either a multiplication operation or addition operation is a less than operation, right? So as I already told you, multiplication is much complex operation than adder or any other operation. So for this particular design, your clock speed will be determined by the delay of this multiplier, right? Because that will be the maximum combinational delay, right? Plus the interconnection, if there is a marks at the input of the multiplier, so that will also come into picture, but that those are very negligible compared to the delay of the multiplier. Okay, so
Yes.
so it
So,
depends on that delay. Yeah, please.
my doubt is, for example, in this example only, you said that, for example, a multiplier takes 10 nanoseconds and
Hmm.
adder takes 1 nanosecond. So,
Hmm.
is it possible to make the clock period 1 nanosecond? That way, there will be no delay for the adder.
Yeah, so then you have to make your multiplier 10 cycle operation,
Yes, 10
right? Because
cycles. Yes.
if you are able to design a multiplier which is 10 nanocycle, that is the fastest multiplier possible. In
So, this
that
is
case, you have to
example.
make, yeah. So you have to make, so you can actually run these things in 1 nanosecond. I mean, or say 100 or say 1000 megahertz. But in
No, so
that
my
case,
question is like if we can reduce the clock period to the operation which takes the minimum time. For example, adder takes only 1 nanosecond. So if you make the clock period 1 nanosecond, then adder will not be idle for any time.
yes, yes.
That is my
So
question. If it is
yeah, so
possible.
yeah, so that is the objective always. So basically, people try to do that way only. That they make this complex operation multi-cycle and try to see the minimum operation like adder subtractor in one cycle, and they try to design that. But you have to understand, once you go into little bit, I mean, try to dig your digital design concept. So once you try to do these multiplications in 10 cycle versus one cycle, the internal structure will be a little bit different, because you have to store the intermediate results, some register will be put in. But if you just assume that those things is not beyond our I mean, purview in this course, we don't have to go into that detail, but we can assume that there is a multiplier given to me which is 10 cycle. So whatever the internal structure is already built up, we can utilize that multiplier. Okay, but you are right that you can actually execute the things in 1 nanosecond based on the minimum time needed for a the block like adder. Okay.
Yes.
Okay. So now this scheduling based on this as I told you, if you try to optimize the area, your latency will increase. If you optimize the latency, your area will increase. So this there is a trade-off. So based on that, there are three type of scheduling. Okay. One is called unconstrained scheduling. Right? So unconstrained is basically there is no constraint. So I don't have any constant for say area, and only thing I have to do, I have to make sure that my schedule satisfy my dependency constraint, right? So the dependency must be satisfied, and then I try to schedule the operation. I mean, whatever the area comes, I am okay, I don't have any problem, but my objective is to just make a scheduling which satisfy the dependency, which is called unconstrained scheduling. Okay, so obviously you understand that this is something you have no control on the area, uh, and similarly, this may not be that good, but we try to utilize this for doing something else. I'll explain, but this is something I'm going to discuss only scheduling in this category today, but we'll show that this particular unconstant scheduling, the results can be used for doing the other two. Okay, so that's something we'll conclude by today's class. So and then the
Sir,
second category, yes please. Yeah.
So we were discussing about this area latency trade-off, right? Like, is it exactly latency, or we were talking about throughput? Exactly. Like, throughput latency is like a virtue of
Yeah.
like, for
So
example.
yeah. So basically, you are right. I mean, you are perfectly right. It is basically the this clock period, right? And
Yeah.
it basically, once you think, so we can think about the clock speed versus the area. So there is a uh, 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 trade-off. But usually people talked about, if you're so as the earlier your friend saying, I think it's Somik, so that if you say try to run it in this in one clock, that adder in one clock in 1 nanosecond speed, that means the multiplier will take 10 cycle, right? So that means the latency will increase, right? Eventually it will also impact on latency. If you go back to this, say, this diagram, so here if you say try to run this particular example in, say, when your multiplier is 10 cycle, so in this chain there are two multiplier, in this chain also there are two multiplier, there is two multiplier here, so it will take 20 cycle eventually if one multiplier is 10 cycle. So your latency will eventually increase to 20 plus 2 other adders, so 22 cycle. So your schedule time will be not 4, it is basically 22, right? So so eventually, if you try to understand very carefully, is so whether I'm going to run it in 10 nanosecond clock or 1 nanosecond clock, I need 22 nanosecond to execute the behavior. You understand the point, right? So because I need one multiplier is 10 plus 10, 20 plus 1 plus 1, right? So 22 nanoseconds. So my in a fast clock or a slower clock, that is my decision, right? So effectively, it's basically the latency. So eventually, that's why we mainly concern, I mean, this latency versus the area. You understand my point?
Yes, sir. Yeah.
Yeah.
So actually, you are talking about area will increase, like when latency decreases. That because if we had more components, area will increase. That's what you meant, right?
Yeah, yeah, yeah.
Okay, sir.
So basically, if you try to run a faster version, your area will increase.
Okay,
But
sir.
overall time will remain same, only whether you want to run a faster clock or not. That is the important factor. Okay. So yeah, so the second category of scheduling is called MRLC. Okay, so minimize resource under
Sir,
latency.
sorry.
Yes.
So if we run on a smaller cycle, what is the use? Basically, total latency, you are saying total latency is same. Where it is giving us a favor.
It is favor, as Somik mentioned, that you can actually utilize the 10 other cycle to do other operations, right? So if this particular, they say in this particular design, there are a lot of multi. In this example, it is not helpful, but say there are certain cases where there are a lot of addition operations, there are small operations. So instead of making your clock slow, you run the circuit in faster, so that you are in 1 nanosecond clock period. So that means it is basically 1000 nanosecond. You keep your multiplier busy for 10 cycle, but in other 9 cycle you do other 9 addition operation. So basically in one, so suppose if this design only you have only one multiplier, say this is the only multiplier and these are all say adder, right? So these are all say adder, and there are many others adder here, right? What I can do, you can utilize the multiplier busy for 10 cycles, right? I can keep my multiplier busy for 10 cycle, and I can actually keep doing the other addition operation here, right? So I can do the addition operation in parallel. See, so then I will have a benefit. So although I need still say 10 nanosecond to execute the behavior, but I can do all other operation in parallel with this multiplier. So I'm not going to keep this multiplier in all other operation or all other modules also busy for 10 nanoseconds. You understand the point, right? So it's basically multiplier won't give you any benefit, but if I make the clock faster, my faster operation can execute in parallel and they can complete by the time multiplier is done. Did you get my point?
Yes, sir.
Yeah. Okay. Yeah. So the next category of scheduling is called MRLC. That means minimize resource under latency constant. Is very try to understand the term very carefully. So my latency is given. Latency constant is given. That means I want to execute this particular behavior under say k number of clock, right? So that is given. So you have to execute the behavior in say k clock cycles. You minimize the resource for that. You may have 100 possible solution which actually satisfy the target clock with target latency constant, say it is k. You give the solution which give you minimum resource. Okay, so under the MRLC, objective is not to reduce the latency, rather reduce the resource, reduce the usage of resource. That means minimize the resource under latency constant. Okay, and the third category of problem is the reverse. It is MLRC, right? So minimize latency under resource constraint. So suppose I have given you the resource constraint. I have 2 multiplier, 1 adder, and so on. There may be many possible solution. You give me the solution which take less number of time step or less latency, right? So which actually take the minimum latency under the given resource constraint. Okay, so that is called the third category of problem that you meet. So here in the third case, you are eventually reducing the latency. Your objective or goal is basically minimize the latency, and your resource is given. You cannot utilize more resource than the given resource. What you can do, you just give me the solution that take less number of time steps. Okay, so that the three category of scheduling problem in general. Obviously we'll take say 4-5 classes to cover all those algorithms. Today we'll take the simplest one, the unconstant scheduling. In the unconstant scheduling is basically, as I mentioned, there is no resource or latency constraint. Only the schedule should satisfy the data dependency. Okay.
So when we are referring to resource constraints here, are we referring to only like hardware, or are we referring to also performance constraints that because it's especially since the architecture is so small, it can only run for so long before it starts becoming too hot in that sense?
Can you repeat your question? I mean, I could not understand.
I'm saying that when we're talking about resource constraints, are we referring to only constraints in the form of we have 10 multipliers available to us, or are we also talking about energy constraints that we can only run something for so long?
Yeah, so yeah, it's a good question. So far it's a number. So how many multiplier is given, how many adder is given. Obviously, you can always take the other constant into a picture, that if I have this category of multiplier of say of this energy, I have this set of multiplier which is basically takes this number of clock cycle, but it consumes this number of energy. So those we can actually advance your scheduling strategy to take care of that, but we try to discuss the very simplest version. The number is given, and one type of multiplier, only one type of solution is possible. Okay, for example, if you just think about the adder, when you have a carry the full adder, right, which is take in number of delay is very high, then carry look ahead adder, ripple carry adder, carry sensitive adder. So there are 4-5 of adder I only know, right? There may be many more. So if you say ki, is the all possible category of adder is available with me, I'll say the kind of solution I am going to discuss, I'll only assume the one kind of adder is given to us, either it's whether it's a carry look ahead or it's a C, but only one type. But you can always enhance this algorithm, and that's going to be a good problem to solve. Is basically, suppose in under the adder category also 4 type of adder is there. One is energy sensitive, one is area sensitive, one is fast clock sensitive, and so on. Similarly, you can have multiplier also, various, right? Boost multiplier, there are Karasua multiplier, and many others. So those subset or say the various optimized version of the multiplier or adder, I'm not going to consider, but yes, it's a good way to enhance this solution in those direction as well. Okay.
Okay, sir.
Yeah. So the simplest method, the unconstant scheduling, as I say, this all operations, the delay is given, that how many time step it will take to execute, and cycle time is given, and then there no constant, basically there is no bound on area, and obviously you you try to satisfy all the dependency constant, but obviously you try to minimize the latency. So under this unconstant scheduling, you try to, there is no bound on the area, so you make sure that you satisfy all your dependency constant, and then your latency will be minimum. Okay, so that is what is the simplest way of thinking scheduling. and which is called unconstant scheduling. Okay. So let us try to formulate the problem more clearly. So as I mentioned, and I have a sequence graph where I have v number of operations. Right, each node is the operations, which I mean is the set of this v. Right, that set of nodes in the graph, and each of the node has a delay d. Right, so it may be 1 because in the example that I have taken so far is the delay is 1, but it can be 2, 3, 4 as we argued so far, right? And we also have this E is the partial order of operation or the data dependency. So E is basically the age define the data dependency or the partial order of these nodes. Okay. And what this scheduling does, it just map those operations to an integer, the start time. Right? It's the integer leveling of the operation, which is called scheduling. So each operation is mapped to some number, right? So if say the operation 1 mapped to 1, that means operation 1 is going to schedule in time step 1 or the start the execution from time step 1. So operation 5, then if the number is 10, that means operation 5 will start the execution from time step 10 and so on, right? Such that it's basically for each this is the ti is the start time, right? Start time is ti for the operation. So this whatever this number, that is the start time of the operations. And if there is an age, so if say this is my node vi and this is my node vj, say this is my node vj, and there is a age from I to j, and say this is this scheduling ti, right? And this will take di number of time step, right? So it will take ti to di minus 1, right? So till some ti to di minus 1, these are the time steps this will going to execute. So I can only execute this guy in this tj. The start time of tj must be should be greater than equal to this number, right? So ti plus di, right? So it should be greater than equal to. So this is what is talked about here. So but here the age is considered vj to vi, but I just explained with vi to vj. Basically the idea is that I can assign any time step, so ti to this guy and tj to this guy, but I have to make sure this tj is large enough so that this operation finishes execution, right? So if this operation schedule at time step ti and its delay is di, it will take ti to ti plus di minus 1. These are now till this point this will be executed. So I can only schedule this operation earliest is ti plus di. So my tj should be tj must be greater than ti plus di. Okay. So this is what is this unconstant scheduling, but it satisfies the partial order, right? Partial order of the operation as well as the delay of the operation. And your goal is to make your tn. Tn is what? Your the time step of this this source, the sync node, right? So the time step of this node is tn. This is always tn and this is always t0, right? So the tn is minimum. So if tn is minimum, that means this is it actually achieves the minimum time step to schedule the operation, because I can only schedule tn when all things are done, right? So I can only schedule tn when everything is done. So if tn is minimum, I can ensure that this schedule is the minimum schedule. Okay. So you try to understand this carefully. This is under minimum latency unconstant scheduling. I want to assign a integer value to each operation, which is the start time of the operations, and which will satisfy the dependency constraint and the delay of the operations. And my tn is minimum, which signifies this is the minimum latency scheduling. Okay. So any doubt here?
So could you explain the partial order? What does the partial order means?
Partial order is the data dependency. That's all. E. So basically, if you think about a graph, right? My sequence of graph is basically G equal to V and E, right? So G is basically nothing but set of node and set of edges, right? And V is nothing but my operations. And E is the data dependency, which is called partial order, right? So what is the partial order among the nodes of the graph, and which is nothing but the data dependency. So you can, instead of partial order, you can just write it's the data dependency among the nodes. Okay.
Okay, sir.
Okay. So the schedule objective is clear to everyone. I hope it is very simple. There are two such algorithm which is called ASAP and ALAP. So as the name suggests, is as soon as possible, right? So this is ASAP. Similarly, I can have an algorithm called ALAP, as late as possible. Okay. So these two algorithms I'm going to discuss in today's class, and then we'll move on to the other MLRC and MRLC. So what is ASAP? So in this graph, I have given this sequence graph VE to me, and your objective is to schedule the things in minimum time step. So I have to make sure that I have done everything in minimum time step. Okay. So if you just remember, so what is the best way to do that? Whenever a particular operation is schedulable, you schedule it. Right? So as soon as the operation becomes schedulable, you schedule it. Right? So that's the idea. So what does it mean schedulable? It is schedulable means all its predecessor operations or the operation on which it was depending earlier is done. Right? So if we just, whenever the operation become available to schedule, you schedule it. So that's the idea. So the algorithm is very simple. You can see here the V0 is my sync node, right? So I'm just saying it is 1, but you can assume 0 also, right? It depends on your convention whether it's a 1 or 0. I mean, the way I look into this, my sync node is always assigned to time step 0, so that this time step 1, 2, 3 will be my operation gets scheduled. Okay. So what I'll do, I'm going to do this. So I'll find out the vertex whose predecessors are all scheduled, right? So if you think about this example, so whenever I just I just assume this, my T0 is 0, that means my this sync node is already time scheduled in 0. So this is my time step 0. So whenever this is done, all these 1, 2, 3, 4, 5 nodes are available to schedule. And in ASAP, I'm going to schedule all of them in time step 1. That's the idea. So whenever this all are done, so this set of operations will become schedulable because their all predecessors are already scheduled. So I'm going to see all the operations that are available to schedule. I'm going to schedule in the next time step. So this is my time step 1, this is time step 2, and so on. So after this, only this operation is ready. So I'm going to schedule this in time step 3. This I'm going to schedule in time step 4, and this Tn will be my 5. Okay. So this is how this ASAP works. So the idea is that I'll identify all the vertices whose predecessors are already scheduled. I'm just schedule this VI, but here the example that I have shown, it is always 1, 2, 3, 4, but it may not be that because it depends on that the delay of the predecessor, right? So what I'm going to do, I'm going to take such VI, and the time start time will be Ti equal to max of Tj plus Dj. That means say there is a node here, say so this is my Vi, okay, and it depends on say 3 such node, right? So there is a dependency on 3 such node, okay, and so they have, so that means it is free, means it's all its predecessors are already scheduled, and their time step is something, and they have Tj plus their execution time in Tj. So what I'm going to do, the start time of this will be whatever the max of this Tj plus Dj, among their what is taking the maximum time, my Ti will be that value. Okay. So basically by setting Ti equal to Tij plus Dj for all my predecessor node. For all predecessor node, I will see what is their start time and what is their delay. I'll take their sum and whatever the maximum time, so that is the time by which his all predecessor will be done, and then I'm going to execute that Ti equal to this value. I hope you understand this. And then whenever it is done, so I'm going to go to the next time step, and you have to understand that since this is a multi-cycle, say suppose I have scheduled a operation here in say time step 1, and it is taking 3 cycle, so his successor, so suppose this is, there is a edge from here. So since I am scheduled this operation in time step 1 and say 3 cycle, it will take 3 cycle. Only at time step 4, this operation will be available to schedule. Okay, that is what is the idea. The select a vertex whose predecessors are all scheduled. It means and their execution is also over, right? Then only I can schedule it. Okay. So this way I can done, and whenever my VN is done, VN is my sync node, I am done with my scheduling. Okay. So this is ASAP, and the ALAP is different. So it's basically it says the as late as possible. So what is the idea? You try to delay the operation as late as possible. So when I'm not going to do it at the time step 1, so I try to defer it as much as possible. So can you tell me how then this will work under ALAP? How can I do that? Because how can I just make sure that an operation is delayed as much as possible, but your objective is to get the minimum time step. So I want to minimize the execution of the behavior or the latency. I want to minimize the latency. So how can we ensure that? So did you understand my point? So basically I want to delay the operation as late as possible, but I want to make sure that I want to execute the whole behavior in minimum number of latency. Okay. So for this ALAP, what we do usually, that we take this G is my sequence graph and a lambda bar, which is basically the minimum time step. How can I get that? My ASAP will give that. So I can prove that this ASAP is minimum time schedule. You can prove it, right? Because it's always early. When try to schedule everything earliest. So if you take this graph, this example, I mean, and if I assume that all operation is single cycle, it will always schedule the things in 4 time step. And you can see the length of this operation is 4, right? 1, 2, 3, 4. So you cannot schedule this particular behavior less than 4 time step. And ASAP always ensure that it will be scheduled in 4 time step, considering the operations are single cycle, right? So similarly, you can actually make a generic proof that ASAP always give you the lambda that you're going to get from ASAP is the minimum time needed to schedule this behavior. So you cannot have a faster schedule for this behavior, whatever ASAP will give you. So ASAP will give you the lower bound. You cannot schedule the things less than that, right? You can prove that, and even you can consider the behavior and some delay, then also you can prove the same thing. Whatever I explained, you can delay of 1, but you can always make the proof generic, and you can actually prove that ASAP schedule is always the minimum can be obtained for this behavior. Okay. So what I can do, because I want to do the ALAP, the idea is that I run the ASAP. I will get the number. Say I get the 4. Okay. So I know that this particular behavior with all operation single cycle, I need at least 4 time step. Okay. And then I want to do the ALAP. So what ALAP will do? I want to execute the behavior as late as possible. So what is the best way to do that? If you start from this direction, this direction, you have no control. Because you have to make sure that things are done in 4th cycle. So what I'm going to do, instead of starting from this node, I'm going to start from this node, loop, the sync node, and I'll just run the reverse logic. Whenever I'll assume that this is going to schedule in 5 time step, because this is 4, that means this will be lambda plus 1. So this is, I'm going to schedule this in 5th time step, and I'm going to schedule all the operations whose successors are already done. So earlier it was when I'm going to execute the operation when its predecessors are done. Here what I'm going to do, I'm going to schedule all the operations whose successors are already done. So if I go by that logic, in time step 4, I'm going to assign these 3 operations, right? Because this operation, these operations, and these operations, their successor is the sync node, which is already scheduled in time step 5. So I can schedule these 3 operations in this cycle. And that is the latest possible way to schedule this operation. This is the as late as possible. This is the latest possible, right? After that, you cannot do it. And then I'll just keep doing this. So whenever I am done with these 3, now I can, in the next cycle, I can schedule this operation, this operation, this and this. So I'm going to schedule these operations in this is my time step 4. Now this is 3. And once this is done, in the next clock, I can do these 2 operations, right? So this is my time step 2, where I'm going to do these 2 operations. And in time step 1, I'm going to do this and this operation. So this is what is the as late as possible, and the whole it is So it needs the upper bound of the latency, which I can get it from ASAP, because ASAP ensures this is the minimum schedule. And then I try to do the scheduling from the reverse direction from the sync node, and just logic is different, that I'm going to schedule an operation when his successor is already done. I can actually do the these operations, and that will give you the as late as possible solution. Okay. So if you look into the algorithm, so yeah, please.
So from a practical point of view, when will we ever need to use ALAP?
It has a lot of use. I'm going to tell you in a minute. Okay. So
So one more thing, why there is need of finding lambda dash? There is, we never used it, right? Only thing is
I'll explain. Just wait for a minute. Okay, just wait for a minute. It will. I'll explain what is the use of this ASAP and ALAP. Okay. So the logic, I hope you understand that I'm going to take the sync node. I'm going to schedule into this lambda plus one, or sorry, gamma plus one. That means the 5. And then I'm going to select those vertices whose successors are already scheduled, as I explained. And then I'm going to schedule this VI by taking the minimum of this number. So here the idea is that if this is my sync node, it can be like this. So I'm going to say, suppose there is a node here which is going to both directions. So now this is the case, and they are both are scheduled. And since they are basically, time step is basically this say this is for VI. So if I start, this is at TI, I need TI plus DI, TI plus DI minus 1 diamond time step. So this must be this TJ must be the minimum of this TI minus DI, right? Because whatever the sorry, this is TJ. Sorry, this TI must be whatever the TJ minus DI. So that will be my TI, and this is for all successors. So if a particular node is I'm going to schedule, I'm going to consider all of his successor and see whatever the TJ. I'm going to go decide TI based on this TI plus whatever the delay of this node. Right? I hope you understand this, because this is how things will work. And then I'm going to conclude this whole process when my V0 is getting scheduled. That means my sync node, right? So that is why this ALAP works. Okay, and it ensures that it will be I mean all operations. So this never return you no, because I know this lambda is my minimum schedule, and I'm just ensuring I'm just doing the operation in scheduling the reverse direction. But since this is already this is obtained from ASAP, I can guarantee that this ALAP always give you a solution, and that is also a minimum solution, because lambda is this gamma is basically nothing but my minimum possible value of the schedule time. Okay. So that's an example of that graph. So this is for ASAP, that I schedule them as soon as possible. I mean, this is I already explained, and this is ALAP. I mean, I'm going to schedule them as late as possible, which I already explained in the previous class. Now the question that Rakesh was asking is why you need this ALAP and ASAP. So can you just notice one thing, that here this operation 11 schedule in time step 2, right? These are all solution based on single cycle, not multiple cycle. Here this 11 is scheduled in time step 4. So in the previous solution ASAP 11 was here, and here this 11 is here, right? So what does it signifies? The schedule time, this is the earliest possible schedule time of 11, and this is the last possible schedule time of 11. So what does it mean? This is the mobility part of this 11, right? So I can schedule effectively 11 anywhere from these 3 cycle, either 2, either 3 or 4, without violating the latency constraint. So this ensures, if I know the ASAP value and the ALAP value, I can guarantee that in the mobility, I can identify the mobility of each operations from this is nothing but ALAP minus ASAP, that band, which is the safe zone of that operations. Even if I schedule this 11 in any cycle in this 3 cycle, I can still achieve 4 clock, latency of 4, assuming all operation is single cycle. So that is the advantage. So we always calculate, we never use, I never design a hardware using ASAP and ALAP, but I always do calculate ASAP and ALAP value, and I make a minus of these two value, and from that I understand what is the zone or the range of value where I can actually execute that particular operations or the mobility. So as I mentioned that ASAP or LAP never get used in practice, but they get always used in any algorithm. We always use ASAP or LP in background to identify their the earliest possible schedule time or latest possible schedule time, and identify the mobility or the kind of zone where I am going to execute this operation, and based on that I can actually take other decisions when I am going to talk about the latency constant, I mean resource constant scheduling, right? So there I can actually think about I'm going to schedule whether I'm going to schedule 11 here or here or here, which actually take less number of resources. Right? That's the advantage of this ALP. Okay, so I'm done. So any question, I'll be happy to answer. Any question?
So